We talked about a couple things. We did talk about the idea of phase changes. And remember that as we transition from one phase to the next, there is a certain amount of energy associated with those transitions. So as we go, say, from solid to liquid or liquid back to solid, that is our heat of fusion, which is sometimes referred to as the delta H of fusion. And that is really the energy, as we talked about, required to change the substance from the solid state to the liquid state, our liquid state to the solid state. Remember that this happens at the same temperature. So we're not changing the temperature or anything like that. We're just simply changing the phase of the substance. That happens at the normal sort of melting point, freezing point of a substance where we get that transition that occurs. We also talked about the transition from liquid to gas also back to liquid. There is also this similar amount of energy required to do nothing more than change the phase. That is the heat of vaporization, or delta H of vaporization is sometimes referred to. We saw the values there for water, for example, and it was, roughly 335 joules per gram, or about 6.02 kilojoules per mole. And for the heat of vaporization, it was about 2260 joules per gram, or about 40.6 kilojoules per mole. And remember that it doesn't really matter sort of which way you're going, if you're going from solid to liquid or liquid to solid. The amount of energy to do that's going to be the same. It's just the sign's going to be different as we're going from solid to liquid. That's going to be an endothermic process. So that should be a positive sort of value. As we go from liquid to solid, that's an exothermic process, which means that the number would just be a negative number. Same thing as we go from liquid to gas and backwards. Really the same numbers used, just the sign is different. We also see here, and as we talked about last time, and as we saw with that calculation that we did, it always does usually require a lot more energy to do that transition from liquid to gas, as opposed to, say, solid to liquid. Again, we're kind of completely separating everybody as we go from liquid to gas, so it takes a lot more energy to do that transition than the other. We did also look at sort of a heating cooling curve type situation, and look something, like this perhaps. And the one we looked at was for water. So we had ice, which is really the solid state. We had liquid water. And then all we have up here, we had steam. And that obviously is the gas state. These sort of transitioning points here, which are sort of flatlined-ish, is I'd say 0 degrees for the case of water. Over here, right, this would be something like 100 degrees Celsius. So when we're talking about our heat of fusion or heat of vaporization, as we talked about, it is always these sort of flat lines. If you look at this little graph, where we again change the phase but not the temperature, that's going to be our delta H of fusion there. And here is again where we would use our delta H of vaporization. Remember that on the other parts of the graph here are really parts where we are, for example, in this area, sort of in this area here, and also in this area here. Those are all, depending on where you're at, if you're anywhere in this area, anywhere in this area, or again, anywhere in that area, um, they are all really in the same phase, but the only thing that's happening is we're changing the temperature. And whenever you want to sort of calculate the heat associated with something where it's in the same phase, but the temperature changes, that was our old friend there, specific heat that we use to do that. So we would use the specific heat equation really for any situation where we have that going on, where it does remain the same phase, but we do change the temperature. So I think we did the one where we took it from ice all the way up to steam. It's really different sort of steps along the way to do that. You figure out the energy associated with each of those steps, and then you can get the total energy really by just adding everything together, all the steps there. And as we also talked about going in the opposite direction, for example, if we did start a steam and work our way down to ice, really, again, the only thing that would be different is the negative sign. Basically, everything would be exothermic and energy being given off. We also talked about intermolecular forces and intramolecular forces. So we talked about intramolecular forces. And intramolecular forces are those forces that are within a sort of single molecule or atom that keeps it together. So, for example, again, if we took out just one water molecule, the intramolecular forces here are really the covalent bonding that's happening between the oxygen and the hydrogen, the sharing of electrons that occurs. In terms of intramolecular forces for ionic compounds, it's really that electrostatic attraction, the positive negative attraction that kind of holds an ionic compound together. Those are, as we talked about, probably the strongest forces that you can have, especially that electrostatic attraction. And they do pale in comparison to the other type of force that we mainly talked about, which is intermolecular forces. And intermolecular forces are how one molecule basically interacts with another molecule. And pretty much all intermolecular forces, as we talked about, is really a basic attraction of the positive side of one molecule to the negative side of another. So pretty much all intermolecular forces is pretty much that's how they interact with each other. Um, they are always weaker than intramolecular forces. And again, it's because that force is basically holding those molecules together, and that would be the first force that basically breaks. We talked about hydrogen bonding as an intermolecular force. That is a bond between hydrogen and really an electronegative element like nitrogen, oxygen, or fluorine. Remember that just because something has a hydrogen in it, it does not necessarily have the ability to hydrogen bond. It needs to be directly bound to one of those guys to have the ability to hydrogen bond. And that is, for example, like water uses here. When we have water molecules, the hydrogen is more positive on water. The negative is on the oxygen here. So when a couple of water molecules sort of get together, the positive of one is going to bond there to another, and that would be hydrogen bonding. These hydrogens can participate in hydrogen bonding because they are directly attached to those oxygens, so they have the ability to do that. And really the reason for that is because when the hydrogen is attached to either nitrogen, oxygen, or fluorine, those are like your three kind of big electronegativity type elements. You'll get a pretty good separation of charge, which means you'll have kind of like a positive side and a negative side that allows it to sort of interact really well with each other. That is probably the strongest, as we talked about, in terms of intermolecular forces. It is, again, pretty much the main force that polar molecules, and again, we're talking about molecular polarity here, the overall molecule that uses when they can hydrogen bond. In addition, there's dipole-dipole interaction, and dipole again really comes from when we talked about bonding dipole moments, which is what polar molecules have. And this is a really strong force as well. This is the main force for polar molecules and other polar molecules, basically, are this themselves as well. And because they have a dipole moment, these polar molecules will always have that separation of charge. So when these two guys get together, they have absolutely no problem interacting well with each other through that sort of opposite attraction. This is the typical main one for polar molecules that really cannot hydrogen bond, for example. So these guys that lack the ability to hydrogen bond, these are going to be our guys that are going to use dipole-dipole as their main interaction. I think we saw in that animation like SO2, which again is an unsymmetrical geometry, and a polar molecule. So something like SO2, which is polar, has no hydrogens to hydrogen bond with. It will use this dipole-dipole interaction, where our oxygens are more negative, our sulfur more positive in this case. And that is sort of how, again, that they're going to interact with one another. The weakest of all these sort of intermolecular forces is really dispersion forces. And dispersion forces are the, as I mentioned, weakest. And they really are the main force for nonpolar molecules. So remember that, as we talked about in a number of chapters, when we have a nonpolar molecule, they basically have equal sharing of electrons, which overall means that it's pretty much going to be like a neutral sort of molecule. There is, again, no side that's more positive. There's no side that's more negative. So since all intermolecular forces basically interact through that positive negative interaction, that's sort of problematic for these guys. So the problem with this is it needs something to happen to cause it to temporarily gain a charge. And there's a couple of ways that that could happen. You could do, as we talked about, what's sometimes referred to as an induced dipole. And in an induced dipole, what you do is essentially something with a charge comes near a nonpolar molecule, and something like an ion, something like a polar molecule. So, for example, if we did back up a polar molecule here to a nonpolar guy, temporarily what that's going to do is the electrons in the nonpolar guy are going to be, again, attracted to the positive side here of that polar molecule. And that's going to create a situation where temporarily our nonpolar guy will get a little separation of charge. And now, they're able to sort of interact with one another in that vein. Polar guy kind of floats away, electrons kind of go back. It's going to kind of not really be able to maintain that interaction. Now, the other way that's probably more common as well, and especially what happens when nonpolar molecules with themselves or nonpolar molecules with other nonpolar molecules get together, is what is sometimes referred to as an instantaneous dipole. And an instantaneous dipole is the idea that in a nonpolar molecule, let's say we had two of them, because the electrons are basically flying around, it is possible that at some point, all the electrons sort of all end up on the one side of the molecule versus the other. And if that was the case for the guy on the left, it would temporarily, once again, create a charge sort of situation for our nonpolar molecule. And if that guy still happens to be next to another nonpolar molecule, the electrons in this case would be attracted to that positive charge and now create a temporary separation of charge in that second nonpolar molecule. And now these guys that originally started with really no way to sort of interact with each other have now temporarily created a way, because of these electrons kind of going one way or the other, to be able to interact with each other. This is what is sometimes referred to as polarizability. That is the ability of the electrons to sort of kind of go one way or the other and sort of distort the electron cloud temporarily. This creates a bond that they can do. It again is all these guys for dispersion forces are really weak in the sense that it needs this to happen. And if something does happen, like for example, the electrons kind of go back to their normal sort of distribution, they're not going to be able to maintain that interaction between nonpolar molecules. So that is very different than what we talked about with polar molecules, which no matter what you do to them, always has that separation charge, which means they're always good to go in terms of bonding. So these intermolecular forces are really important in terms of a few things. When we talk about these intermolecular forces, they are really the reason why we have certain melting points or boiling point temperatures, also in terms of solubility, how things interact with other molecules. So if you have a really strong intermolecular force, like somebody's able to hydrogen bond, you typically would expect that guy to have a high melting point and boiling point because they're going to be held together a lot stronger. It's going to take a lot more energy to kind of pull them apart from each other, just for example, go into the gas phase, as opposed to if something's using something like dispersion forces, which is a relatively weak intermolecular force. You would expect them to have a much lower melting point and boiling point compared to something that's able to hydrogen bond. Now, even though, again, as we talked about, dispersion forces are weak, the strength of a dispersion force does increase with molar mass. So if you're comparing two nonpolar molecules and again want to know which one would probably have the higher boiling point or even the lower boiling point, whichever way you want to think about it, the one that is the greater molar mass would most likely have the higher boiling point. And that's because more molar mass, more atoms, more electrons, and also a lot more places where interactions can occur, and that makes sort of a stronger, weaker type force that occurs. In terms of solubility, it has a dramatic effect on solubility of things because typically things will interact well with other molecules that are using the same type of intermolecular forces. If they're using very, very different intermolecular forces, they typically will not interact well with one another because they really have no way to keep that interaction going. Any questions on any of that stuff there that we talked about last time? All right, so last few things out of this chapter, I think a little bit about solids. We're not going to get too deep into solids, but we'll talk just a little bit about it. Good talk. Let's go back. All right. So a lot of substances are what are referred to as crystalline solids. There's two types of it. There's ionic solids, which is sort of what you have in ionic compounds, so things like sodium chloride. There's also molecular solids, which are, for example, things like sucrose. Certain solids, like ionic solids, have long range order, which that means is you could kind of take like an ionic compound and you could cut out like a little piece of it. And just from that little piece of it, you could really recreate sort of this three-dimensional structure because it has very much a lot of repeating patterns. So for example, a lot of ionic compounds are like kind of put together in a three-dimensional sort of way, positive, negative attraction. And you could take like a little snippet of how they are put together, and it is so repeatable that if you just had something like this, which is sometimes referred to as a unit cell, that has information about how the atoms are put together and how they are related to each other, you could just keep repeating this pattern and just kind of keep on repeating this pattern. And eventually, as you can kind of see here, you pretty much can recreate this exact structure just from that one little piece of pattern. So it has very long range order. It's able to sort of repeat very, very well. A third type of crystalline solid is an atomic solid, and that contains one type of an element that's covalently bonded together, like graphite, boron, silicon, and all of the metals are atomic solids. So here again is that sort of ionic solid here. And again, it does have pretty long range order. As you probably could guess, the larger guys are our chlorides, which are negatively charged, and our smaller guys are our positive sodiums in this case. And that is related to the idea, right, that if it becomes positively charged, it has lost electrons and the overall size gets smaller, right? And if the negative chloride there gained electrons, its electron cloud is going to get larger. So again, that's why we have the larger circles for the negative guys, smaller circles there for the positive guys. This right here is some different arrangements of these type of solids here. This is diamond. And again, this is sort of all the same element there, an atomic solid. Here's our ionic solids kind of arranged in that ray. And here is ice, which is arranged in almost layers. And again, as we talked about also in the last chapter, in the solid version, as they kind of layer up like that, We do get all that kind of open space between the different water molecules, which again accounts for the lower density that we talked about earlier on in this chapter. Now, bonding in solids, ionic solids are held together by that electrostatic attraction. Again, as we talked about, that's like an intramolecular force. That's a really strong force. And typically they will have high melting points. As we talked about, when we talked about with gases, typically ionic guys will not go into the gas phase. They actually will just typically melt. So you can heat the heck out of an ionic solid, and even heating the heck out of it will not get it into the gas phase. Again, it will just probably start to melt as we see here when you get to those really high temperatures. Molecular solids are held together by basically intermolecular forces. They typically will have a much lower melting point temperature. So again, the difference here between how these guys are held together, we have intramolecular forces on the top guy and intermolecular forces on the bottom. And that's again going back to that simple example of water as a molecular solid, which is ice in this case. Um, and that's held together really by hydrogen bonding. So that's, although it's a really strong intermolecular force, it is again not as strong as the covalent bonding that's happening within the water molecules. And we will start to break those guys and have a much lower melting point. Now, bondings in metals, there's a couple different types of metals, and one, we can have an alloy, and that is a substance that contains a mixture of elements and has metal properties. There's a substitutional sort of alloy, and that's where the host metal is basically replaced by other metals of similar sizes. So, for example, sterling silver is mainly silver, but some of the silver atoms have been replaced with copper. Interstitial alloy is formed when there's kind of holes between the metal atoms, and those holes are occupied by kind of smaller metal atoms as well. Steel is an example of that. Is mainly carbon atoms in the holes between the iron. So it has mainly iron, and in between the little irons kind of holes that form between them, you have this other element in there, which are carbon atoms in this case. And we have some pictures of that, I think, here. So here's our brass where we kind of swap out some of our copper with some zinc, and they're basically the same size. Here is steel where it's mainly iron, but in these little kind of crevices between the different sort of iron molecules, we have these carbon guys. I'm sorry, carbon guys inserted in there in its place. 11, I think. All right, so chapter 15 is up next, which is solutions. It's kind of like that experiment we did last week. So we'll talk about some of that stuff in that second experiment. So let's talk about solutions. And as we've talked about previously, a solution is an aqueous substance, and they're typically the ones that get the AQ symbol next to them. A lot of important biological reactions happen in this sort of water environment or aqueous type of environment. And a solution is a homogeneous mixture of two or more substances. And there's really two parts to a solution. There's the solute, which is the smaller part of the solution. And there is the solvent, which is a larger part of the solution. Typically, the solute is dissolved in the solvent, and it will dissolve completely because it will make a homogeneous mixture, and that will give you your solution. So a reminder that there is a difference between liquid and aqueous. So liquid is a pure liquid like water, which is a pure substance and a liquid. But if you do take water, which is a liquid, and mix it with some solid sodium chloride or salt, we do know that the sodium chloride will dissolve in it, and it will give you a sodium chloride solution that gets the aqueous symbol. and that's going to be a homogeneous mixture. Here, this is going to be our solute, and in this case, this will be our solvent in this case, which is our water. If you're not sure what the solute is in a solution, it's a really simple way to figure it out. It's pretty much the name of the solution. So whatever the name of the solution is the solute that it's in there. So if you had a potassium chloride solution, potassium chloride would be the solute. Most likely, water would be the solvent. If you had a sodium nitrate solution, then sodium nitrate would be the solute, and probably again water would be the solvent. Water is the solvent for a lot of things. A lot of ionic compounds water is a really good solvent, but there are situations where water, as we will talk about, is not a good solvent. So although it is a solvent for a lot of things, it may not always be the solvent for a particular situation. So you do need to have both of those things, the solute and the solvent, in order to have a solution. Water works well as a solvent, for example, for an ionic compound because of what we were just talking about previous chapter, which is water is polar. And again, when we think about water, oxygen is more negative, hydrogen is more positive. So really, when we dissolve an ionic compound in water, it does what we talked about last time, which is sometimes referred to as a ion dipole interaction that's happening, which is an intermolecular force. And because water really has a positive side and a negative side, it works really well when we put some type of ionic compound in it, because we will get basically two ions that are going to be there. And the negative side of water will be attracted to the positive ion. And the positive side of water, which is the hydrogen, would be attracted to the negative ion. And this is essentially how something dissolves in water. Basically, there's a bunch of water molecules. It just grabs out each of these ions from its ionic solid. We usually help this along the way because when we go to dissolve something, we usually mix it, right? And as we're mixing it, we're throwing water molecules all over that solid. So it's having a lot of water molecules all over the solid, also adding a little bit of energy as you do that as well. So that's going to help those water molecules basically pluck off each of these ions along the way and be able to surround them. And you'll have a lot of water molecules surrounding these guys using ion dipole interaction. And it does two things. It visually, for us, when this happens, means that we no longer can see the salt, for example, it will dissolve. And it also keeps those two ions away from each other because they have a really strong attractive force to one another. But because they're surrounded by so much water, it is no longer visible to us, and it keeps those ions away from each other. We know that they would definitely want to come back to each other because we've done this experiment way before at the beginning. When you take some type of salt water, for example, and you heat it up, when you start to heat up the salt water, we again are going to evaporate off all these water molecules. And once those water molecules basically evaporate off, there's now nothing in the way for these two guys to come back together. And you will again see that solid reappear. This is also why what we talked about, a mixture is a physical change, right? So although we cannot see the sodium chloride anymore, there is no chemical change happening here because it's still there. And we can get it back by just simply evaporating off the water. So remember, again, more of a physical type property, right? When you make a mixture, and since a solution is a homogeneous mixture, which again means that everything looks the same throughout, this is all sort of a physical process that's basically occurring. And that's essentially what's happening here. That's our ionic solid in the solid state. Again, with all the water molecules coming in, they're going to grab off all these ions. Once again, you're going to kind of help it out by and relaxing slow-mo animation of that happening. You're going to help it out by throwing the water molecules all over that solid. And again, as you can see, they're going to block one off.
Water because of its polar nature. Notice how water molecules become attached to the ions of a sodium chloride crystal in the process called hydration. Positively charged sodium ions attract the partial negative charge of the oxygen in water. A similar attraction occurs between negatively charged chloride ions and the hydrogen atoms, which have a partial positive charge. These interactions loosen the attractions between the ions in the crystal, dislodging them from the crystal. Additional water molecules surround the released ions, insulating them from attraction to other ions.
So again, there's just obviously so much water molecules that is able to actually kind of rip those guys off away from each other. And like I said, you help it along by adding a little bit of energy and allowing the water molecules to hit everybody. So how things interact with one another, again, is related to the type of bonds that we've been talking about in some of these previous chapters. Hopefully we still remember this. An ionic bond obviously is between a metal and a non-metal. Remember, that is where we get electrons that are transferred and we create ions that are attracted to each other through opposite charges. And that's different than sort of covalent bonding, where we definitely have sharing of electrons that are occurring. The reason, again, we really do get sort of sharing of electrons and covalent molecules versus ionic molecules is covalent molecules typically, or molecular molecules, are typically between two nonmetals, which have very similar electronegativity and periodic type trends. So as we talked about, the best that they're going to do is share those electrons. We get the full transfer of electrons, right, in an ionic compound because we have that metal, non-metal together, which have pretty much opposite periodic trends in terms of what they want to do with their electrons. The metals pretty much want to get rid of their electrons. The non-metals want to accept them. So we get that transfer of electrons that occur. And obviously with our covalent bonding, we get either a polar covalent bond, which is unequal sharing of electrons. That creates our polar molecules in a lot of cases. And that will get us perhaps a dipole-dipole interaction or hydrogen bonding that's possible. In a equal sharing of electrons, that might result in a nonpolar molecule, which again will give us really no separation of charge. All right, and obviously our polarity depends on our electronegativity and the difference in electronegativity, as we talked about in the bonding chapter. So let's talk a little about solubility of things in water. And obviously, if something is soluble in water, what that means is it will be able to interact well with water. So one of two things could happen, right? If we're talking about something being soluble with water, if we're talking about a solid and water, that means that the solid will dissolve, right? Now, if we're talking about something being soluble with water, like a liquid and water, that basically means that they will mix. So what that would look like, say, in a test tube is it would all look like one layer, right? We wouldn't see any type of layering that's happening. As opposed to if we took a solid and water and they did not mix and they were insoluble, we would not get it to dissolve. You would still see the solid that's still there. Now, if we took a liquid and water and they did not mix and were immiscible in each other, we would see some different layering that's going to happen, right? Because they will not mix. Again, usually we talk about this up here being soluble. Something that doesn't mix is insoluble. If we're talking about liquids, we sometimes talk about miscible, right? If they are soluble, immiscible if they are insoluble. So kind of a couple of terminologies sometimes used. So when we talk about ionic compounds like sodium chloride, ammonium nitrate, they are definitely going to be soluble in water. Non-ionic substances like sugar and ethanol are actually still soluble in water as well. With our ionic compounds, they are going to do what we just saw there, basically our ion dipole interaction, where basically the ions are going to be surrounded by the negative side, right, and positive side of water, and basically allow it to dissolve. Now, if we look at something like ethanol, which looks something like this, Ethanol is an organic compound. It's an alcohol, and it is the alcohol. It basically has two parts. That is this part here, which is basically made up of all these carbons and hydrogens, and carbon and hydrogen is a nonpolar bond. So this part of ethanol's molecule is really nonpolar. But what allows it to really be sort of soluble with water is the fact that it does have in the front end here, it does have this bond right here, which is really a polar bond. And the oxygen here is more negative, the hydrogen is more positive here. And that is, for example, the exact same bond that you see in water, right? Water has two of those bonds, which means when something like ethanol gets in contact with water, which once again also has the same situation, they're going to have no problem doing a little bit of hydrogen bonding with each other. And that's going to make something like ethanol be very soluble in water. Also, if you had methanol, like the experiment we were doing last week, methanol, which is one carbon and that OH group, basically, it will also be very soluble in water. So they are soluble in water, ethanol, and even methanol because they have this OH group. They're not relatively large molecules, which means the water could kind of get in there and water can interact really well with it, and they will be very, very soluble. Now, sugar, as we'll take a look at a little bit later here in a couple of slides, sugar is a little bit larger of a molecule, but the one thing that sugar has that really helps with its solubility in water is it's pretty much littered with OH groups all over it. So it's got a lot of OH groups all over it. And anywhere there's sort of an OH group on the sugar molecule, it gives it the opportunity to interact well with water and do some hydrogen bonding and makes it very, very soluble in water. Now, mind you, if you took something like ethanol, and it wouldn't be ethanol at that point, but if you added, for example, a ton of carbons and you got this OH group here at the end, and all these carbons have hydrogens. And right about now, I'm regretting how many carbons I drew there. Okay. All right. So obviously in this part here, that is going to be nonpolar. But once again, it still has this polar part over here. The solubility of something like that is going to be pretty much nothing. And that is because even though it has that little kind of OH group at the end, it has a pretty big part that's nonpolar. And that is what's sometimes referred to as steric hindrance, which is, I guess, a fancy way of saying that part gets in the way. And it's just so large, it doesn't allow water to sort of get in there and interact well with that OH group. So it'll be pretty much insoluble in this case. Remember that anything that's going to be, for example, soluble in water will have to basically take water molecules that are attached to other water molecules and basically replace those with themselves. So the problem with what I drew on the bottom there is it's pretty large. It has that one little spot. It's not going to be able to interact well with all the water molecules. It's not going to fit really well with water. It's going to be really too big and not really be able to allow water to get in there to interact. Typically speaking, when you look at organic guys like these guys here, like these alcohols, once you hit about 5 or more, 5 to 6 carbons, solubility is pretty much nothing at that point. So it pretty much drops to nothing. With that being said, if you increase the amount of OHs, kind of like in the idea of sugar, it actually will increase the solubility a lot. Again, everywhere there would be an OH group, it would be a place where it can interact. Like if I slapped another OH group on the back end here and replace that hydrogen, it would definitely increase the solubility a lot as well. So here is methanol, for example. Here, they're able to interact through hydrogen bonding. They're able to hydrogen bond with one another. Again, the hydrogen from the oxygen or from the water, hydrogen bonding with the oxygen there, and methanol. There's our ethanol guy that we just did. Now, what about oil and water? Do they mix? They really do not mix. And that's because pretty much oil is just a really long chain of just straight carbons attached to carbons and carbons attached to hydrogen. So really a main thing of what oil looks like is, I'm just going to steal that one so I don't feel so bad about drawing it a minute ago, is basically if we just took, I just make a big H here. I just took this part of it, all those carbons and hydrogens, that's pretty much what oil is. It's no OH, nothing on it. It's just a bunch of carbons and hydrogens basically attached to one another. And because oil is pretty much just that, a big old thing of carbons and hydrogens attached to each other, because carbon-carbon bond is nonpolar, and definitely the carbon-hydrogen bond is nonpolar, it has no way to interact well with water. Because it is nonpolar, oil is going to pretty much want to use dispersion forces. And that's very different than water that wants to use hydrogen bonding. So those are two very, very different types of intermolecular forces. And over the long period of time, they have no way to maintain that interaction. So what usually happens is the oil will separate out from the water, right? And oil will end up where? Below the water or on top of the water? It will end up on top of the water, right? And that's because it's pretty much organic and nonpolar and it will float to the top there because it's less dense. If you ever seen an oil spill right in the water, right? You see the oil just kind of floating around, right? That's how they know there's a leaky pipeline underneath, like if there's a sheen on top of the water kind of moving through it. And that's because over a long period of time, the oil cannot keep that interaction happening. Can it interact for a short period of time? It can, but again, over that long period of time, they're just going to eventually kind of separate out from each other. There's no main way to maintain that over a long period of time. In addition, because oil is typically a really large molecule, much like the other thing that I drew there, it is not going to fit really well with small water molecules as you have to replace water molecules with those guys. So I kind of think of it like a garage, right? You can fit a car in a garage pretty good, right? But if you try to park like a semi truck in a garage, you might get part of it in, right? Not going to really fit right. Not going to work really right with your garage, and it's not going to really interact well with your garage either. And that's sort of what happens when you get these really large molecules that are nonpolar using dispersion forces and trying to interact with something that's polar that wants to use hydrogen bonding or dipole. That brings up the incredible idea of solubility, which is this idea of like dissolves like. And basically what that means is all the stuff about how molecules interact with each other in terms of their solubility is all related to those intermolecular forces. So things that have very similar intermolecular forces, they're going to be good to go. They're going to be able to interact well with one another, either through hydrogen bonding, for example, and hydrogen bonding, dipole and dipole, or even dispersion forces and dispersion forces. But when you get things that sort of cross over from like, you know, polar and nonpolar, they have very different ways of interacting with each other. So when we think about things that are going to be soluble, ionic things, and polar things, they are good to go. They're going to do that ion dipole sort of interaction, kind of like what we were talking about with the sodium chloride and water dissolving. When you have polar guys and polar things, they're going to be good to go. Either they're going to use hydrogen bonding, dipole, dipole. They'll be able to sort of interact well with each other. Now, the one that sometimes people sometimes miss is nonpolar things and nonpolar things are also going to be soluble in each other because they're both also using, even though it's a weak type of interaction, they're both still using the same thing, which is dispersion forces. So again, they would be able to interact well with each other. You really only kind of get into a little bit of trouble here when you cross over anything that is polar and nonpolar. again, because we're going to get very different ways of trying to interact with each other. So that is why water is a really good solvent for things that are ionic and for things that are polar, because they're going to be able to interact well with each other and mix. Water would be a terrible solvent for something that is nonpolar. So if you try to take like those iodine crystals and put it into water, it's not going to mix, it's not going to dissolve, because your iodine, which is like I2, right, is nonpolar, and your water is polar, so they're not going to be able to interact well with one another. Any questions on that there? So here is a picture of a couple of those things. Here's our sugar. And again, even though it's a relatively large molecule, it is, as we can see here, littered with OH groups all over it. And again, everywhere there's that OH groups, allows it to interact well with water and makes it quite soluble. Here is a, again, oil sort of molecule. And again, as you can see, pretty much going to be nonpolar, no way to interact well. This is, again, what typically will happen. We'll get that oil separating out from the water. And again, it's not going to fit really well with all the other water molecules that are there to start with. Now, when we talk about solubility, as I mentioned, if one substance, the solute, is dissolving in another, like the solvent, it is said to be soluble. So salt is soluble in water. If we really get things that don't dissolve in, say, water, it would be insoluble. So oil is insoluble in water. There is a limit to the solubility of one substance in another. By the way, the limit on solubility is based on temperature. So typically speaking, the higher the temperature, the more soluble you can get something to be, in terms of like a solid in a liquid. And kind of the lower the temperature, you usually will have a lower solubility of, say, like something like a solid in a liquid. Now, gases are always soluble in each other. The reason gases are always soluble in each other is they are gases, which means by definition, they're flying around, which means they are constantly mixing with each other, right? And some liquids are always mutually soluble in each other. So that's our polar and polar guys are going to be good. Our nonpolar guys are going to be soluble in each other, again, because they're using the same type of intermolecular force. Again, that is the idea of like dissolves like. The solubility of a solute also, again, depends on a temperature. So the higher the temperature, larger solubility of a solid in a liquid. Again, you're providing a lot more energy, right? So that's going to allow things to kind of break apart and mix a lot better. Lower the temperature, we have a larger solubility of a gas in a liquid. And that is because if you have a gas in a liquid, at a lower temperature, our gas molecule is going to be moving a lot slower, which means because it's moving slower, it's going to stay in the liquid part for a lot longer period of time before it's able to basically escape out of the liquid part. In addition, when we talk about gases, it's dependent on the pressure. The higher the pressure, the larger the solubility of, for example, a gas in a liquid. Very common example is the soda can, right? If you have soda, before you pop the lid, you have a lot of CO2 molecules dissolved in the liquid part of it, right? That soda can's under high pressure. And when we have a high pressure, we have a low volume, right? Which means that all the gas molecules are going to be kind of squished down into the liquid part. When you pop the top there, you see all the fizzing coming out, right? And again, that fizzing is really the CO2 molecules that can now escape. And that's all the fizzing that's coming out of the top. Because you did two things there. You pop the top, which release the pressure, right? And release the pressure is going to allow a larger volume for the gas molecules. So they're going to be able to escape the liquid. And also you created an escape route for them to really escape, right? That's why when you go back to your soda later, it tastes flat, right? Because all your CO2 molecules went out the hole, basically, that you created, and it's less soluble in the liquid part at that point, so it's going to escape out the top. Any questions on that? That's what's known as Henry's Law, they call that, I think. Solution composition, there's a couple ways that we classify solutions. So let's talk about those. When you have too much solute in a solvent, that is sometimes referred to as a saturated solution. A saturated solution is basically a solution where you have hit the maximum amount of solute that will dissolve in that solvent at that temperature. Again, it's temperature dependent. So if you've hit a saturated solution, you basically have hit the point where if you try to dissolve any more solid in there, it will not dissolve. It basically will just pile up on the bottom of whatever it is, your beaker or whatever it may be at that particular point. The opposite of that is an unsaturated solution. And in an unsaturated solution, you haven't hit that point yet, which means that you have some room to dissolve more solute. So if you have an unsaturated solution, you could continue to dissolve the solute in the solvent, and it will continue to dissolve. And it will continue to dissolve really until you hit a saturated solution. So you'll be able to kind of continue to dissolve the solute in it, and it will continue to dissolve. You're all good. At some point, once again, you will hit that point, which is sometimes referred to as the saturation point. You'll hit that point where no more is going to dissolve. And at that point, you technically hit a saturated solution. Any questions on that there? Now, obviously, our supersaturated solution, as we talked about in last week as well, is a solution that is, again, a really unstable solution. And it is a solution that has way too much solute or solid dissolved in the solvent. And as we talked about last time, one way that you can create a supersaturated solution, for example, is on this page. So if you want to create a supersaturated solution, you typically would make a saturated solution while you're heating it. So again, as we talked about last week, as you're heating it, you're increasing the temperature, which is going to allow you to get a lot more of the solid to dissolve. So you're increasing the temperature, going to increase the solubility of the solid in the solvent. It will also get a lot more of it to dissolve. So as you're warming it up, it's going to allow you to get a bunch of solid dissolved. And typically what you do after you kind of warm it up, you get all the solid dissolved in it, is you then cool it back down. Undisturbed. You try not to touch it too much either. And you're going to let it kind of cool back down. Now, at this point, once you let it cool back down, the solutions like the solubility of everything you just dissolved in there has now come back down with the temperature. The problem is at this point, it's kind of too late. It's already dissolved. So as we saw with that demonstration I did last week, you have basically a solution at that point, right? And you have a really unstable solution because, again, all that solid has been dissolved at the higher temperature. It's cooled back down, and now you got way too much trapped in the solvent, and it doesn't really want to be there. Anything that you do to it will essentially tell it the solid needs to come out of solution. Very commonly, you could put one little drop of it in there of whatever you dissolved, or in some cases, if you bang it too hard or something like that, once that one little drop will come in, it's like, whoa, too much. And that's going to cause, again, as we saw, all of that solid basically come out of solution and will basically recrystallize because all that solid, there's not enough solvent there to handle it. And that's what we saw here. So let's take a look at that one more time.
The last, the supersaturated solution of sodium acetate in water. A small crystal of sodium acetate will be added to the solution.
So you can barely
Focus
see
your
the
attention on the
crystal.
portion of the solution to which the crystal is added.
So again, as we saw last week, just adding that one
Here is
little
the process
crystal
in slow motion.
Super slow motion. I like the replay. There it is. So again, that one little crystal is enough to really push it over the limit and go, too much is dissolved. And again, that is all the solid coming out of the solvent. And as we saw last week, that's going to be like rock hard at that point, right? It's going to be all solid at that point from the solution that is there.
The flask contains a supersaturated solution.
Any questions on saturated solution, unsaturated, supersaturated solution? Other ways to also classify solutions is concentrated or dilute. A concentrated solution is one that has a lot of solute dissolved in it. That is typically how a lot of solutions are purchased. They come as really concentrated solutions. We then will oftentimes dilute them and give them to you to use in the lab. And a dilute solution is one where we have a relative small amount of solute that is there. It is the classic example of you get the big giant big gulp right before you come to class, right? With all the ice in your soda and you drink it, you leave it in your car. After your classes, you come back out to your car, it's 100 degrees in there, right? All the ice is melted. You still try it because you're thirsty, right? How bad could it be? Maybe you regret it after you try a little bit of it. Maybe you don't. Maybe you like the taste of it. Doesn't taste as great, right? Because you've now flooded your soda and all the syrup, right, with a lot more water that has come from your ice cubes and you've diluted down your soda. We've all been there. We've all done it. Any questions on that there? All right, I think actually it's a good stopping place. Yeah.